Hey folks, so I want to do a worked example. Um, this one is number 54 from chapter 10. It says, a spring shown is compressed 50 centimeters and is used to launch a 100 kilogram physics student. The track is frictionless until it starts up the incline. The student's coefficient of friction on the 30-degree incline is 0.15. So there's no friction on this problem whatsoever, on this incline whatsoever, until we get to the 30-degree incline. And I've shown this a little bit as a red dotted line. We know a few other things. We know that we start 10 meters away from the bottom, 10 meters above the bottom lowest point on our track. We know that our K value, our spring constant, is 80,000 newtons per meter, which sounds ridiculously large, but this is on the order of the size of like a spring constant for shocks on a car. Shocks on a car are somewhere around shocks on a car are about 100,000 newtons per meter, give or take. So this is a beefy spring. So our first part of this problem is, what is the student's speed just after losing contact with the spring? And then we want to know, how far up the incline does the student go? So the first part, let's start off with part A here. With part A, we got some information here. We are looking at what is our speed right at this point, right? This is our part A kind of goal, objective here. What's the student's speed? So we're in chapter 10. It's all about energy. We are conserving energy. We're saying that the change in our total mechanical energy is 0 if we're in an isolated system. So are we in an isolated system? Well, we got a spring. Spring stores some potential energy, right? And we are going to be moving. That's kinetic energy. So far, so good. Are we interacting with the environment? And I would say no. We are not experiencing any external works. There are no frictional forces yet. So everything that we're talking about is internal work, internal to our system. So what I can say here is delta E equals 0. So this is true. We're going to say that our kinetic energy, our change in kinetic energy, plus our change in potential energies is equal to 0. If we break this apart a little bit, I'm going to say that everything that we begin with, so we begin with some kinetic energy, maybe, some gravitational energy, maybe, some elastic potential energy, maybe, that should be equal to the final kinetic energy, the final potential energy, and I'm talking about gravity there, and then the final elastic potential energy. So now I need to actually say, which of these energies do I actually have? Initially, am I moving? No. No, it's compressed, and it's going to launch a physics student. This poor physics student. So I don't actually have any kinetic energy to begin with. Do I have any gravitational energy, gravitational potential energy? I would say yes, right? Where do we want to put our 0 potential energy, right? I think it makes sense to put it right at the bottom here. UG equals 0 at the bottom level. The problem, not a problem, but one consideration that we need to make here is that we don't actually change height when we're thinking about our initial and final positions here, right? So UG stays the same initially and finally. They will cancel each other out. But I do have some initial elastic potential energy, right? We've compressed our spring, so there is some 1/2 K x squared here initially. What does that equal to? Well, we're looking at how fast we're moving, so of course there is some kinetic final, mv squared, F. We said that our gravitational potential energy is the same before and after, so they can cancel out of this entire system. And do I have any elastic potential energy? I don't think so, right? Because I'm looking at when I lose contact with the spring, and that happens at the equilibrium position, the equilibrium length of our spring. And so I don't think I'm going to have any elastic potential energy. I think I have this relationship. All of my elastic potential energy is going to turn into my kinetic energy at this point. So let's kind of quick throw in some numbers. I get 1/2. 1/2. I'm going to say 80,000 newtons per meter for my K value. I know that I compress 50 centimeters, so I'm going to say 0.5 meters squared equals, let's throw the mass on this other side here. I know that my mass of the student is 100 kilograms. That's equal to V squared. If I get rid of the square there and take a square root on this side, what do I get? I end up getting 14 meters per second. So that's the speed right after I lose contact with my spring. For part B, I'm asking, how far up the incline does the student go? And specifically, I think I want to know something about, I actually want to know this distance. I want to know what this delta x is. All right. I'm not actually looking for the height per se. I'm looking for how far up the incline it goes. We can obviously turn that into a height pretty easily, and we may even need the height at some point to talk about that. But let's just go ahead and assume we're looking for delta x there. Again, I'm thinking about this change in total mechanical energy, but this time I do have friction, right? I do have friction, so this is a non-isolated system. This is equal to the external work being done on our system. So I can take this apart. I can say, what are all my initial quantities, right? I can write out all my initial kinetic energies, my potential energies. I'm going to throw my external work on this side. And I'm going to set it equal to all my final quantities. Kinetic, final potential in the gravity, and final potential elastic. So right at the end here, at the tippy top, I'm not moving. My kinetic energy is going to be 0. Likewise, there's no spring up at the top here, so my elastic potential energy is 0 as well. I can't store any energy in a spring when there is no spring present. So everything that's being stored here is in gravitational potential energy. Now, I have a few different starting locations I could have, right? I could say I could start at the very, very beginning, right? I could start at the very, very beginning, and then I have gravitational potential, and I also have elastic potential energy. Or I could start at the point where I lose contact with my spring, where we found our velocity in the last part of the problem, in which case I would have kinetic energy and gravitational potential energy, but no elastic. And I think I might actually go with that. I'm going to say that I'm starting here. All right, I'm going to, let's make a little initial and final. I'm doing this in red to indicate that we're in the frictional portion of this problem. So I have some 1/2 mv squared. We said that v before was 14 meters, plus some mgh, where I think I'm going to be at 10 meters high. We're going to say that we're starting off 10 meters high. So I'll say hi, vi. And then I do some external amount of work, right? Now that external amount of work is going to be the frictional force. So I have some mg, which is going to be my normal force, times some coefficient of kinetic friction, times my displacement up the ramp. But the big thing here is I am at this angle, right? I'm at this angle. So if I actually think about this, my normal force is going to be the y prime component. I need to multiply this whole thing by cosine of 30 degrees. And of course, in the dot product, there's also that cosine of 180 degrees because I'm always going to oppose my displacement. I'm going to fudge that just by switching this positive to a negative and calling it a day. It's a little bit lazy, but it works. What is this all equal to? It's equal to mgh2, right, or h final. The first thing that I notice in moving forward from this is that I have an m in all scenarios here. The m's are going to cancel. And I'm going to have 1/2 vi squared. Let's just clean this up a little bit. ghi minus g mu k delta x cosine of 30 degrees equals g. Now, here's the interesting part. How can I relate hf to delta x, right? Because I don't know hf, and I don't have anything to really solve for that right now. But I could say, well, it's the opposite side to this 30-degree angle. So maybe I could say something like hf is equal to delta x times sine of 30 degrees. I think that works. Now I have two delta x's, so I want to take care of that. I have 1/2 vi squared plus ghi equals my delta x times the quantity of, let's see, g mu k cosine of 30 degrees plus g sine of 30 degrees. Ooh, running out of room. And so I divide that by both sides. I'm left with 1/2. Let's start plugging some numbers in. 14 meters per second, quantity squared, plus 9.8 meters per second squared, times hi, which we said was 10 meters to begin with, all over. G is constant, so let's actually just pull that out. 9.8 meters per second squared times mu k, we said that was 0.15, times cosine of 30 degrees, plus sine of 30 degrees. Let's just check our work there. That all should be equal to delta x. And when I plug in numbers to my calculator, I get a delta x equal to 32 meters. So that's pretty far up. It's not as far up, though, as if we didn't have any friction. We would have made it up a little bit further. Friction did negative work on our system, so it took energy out of our system, put it into the environment in the form of heat, in the form of thermal energy, and as a result, we weren't able to get up quite as high as we do in this situation. But that is a simple example of an isolated system and a non-isolated system in the same problem, and how we would go about them differently. My biggest piece of advice is think about what you have initially, think about what you have finally. and if you are interacting with the environment. Do you do external work? Sometimes it's tricky figuring out where your initial spot is and where your final spot is, so that give some time on that. Give it a second to really think that through. But that's this problem. If you have any questions, feel free to email me or come to an office hour. Have a good one.